Right, hello A-level students. As you can probably tell, this is the M2 paper for January 2010. Okay, so question 1. An object P of mass 6 kilograms and speed 1 meter per second is sliding along a smooth horizontal table. Object P explodes into two smaller parts, Q and R. Q has mass 4 kilograms, R mass 2, and R's got speed 4 in the direction of the motion of P before the explosion, blah blah blah. Calculate the velocity of Q. So this is a relatively standard conservation of momentum question where we're trying to find what direction and what speed is Q going at. So we're going to use the conservation of momentum formula. So in other words, the total momentum before the collision, or in this case separation, has got to equal the total momentum afterwards. So I'm assuming V is going to go right, and I'm just going to take right as positive. So if we get a negative answer, we know Q is going to the left. Right, so the total momentum before, so remember this is always mass times velocity, so it's going to be 6 times 1, and that's got to equal 4 times V plus 4 times 2. So in other words, 6 equals 4V plus 8. So 4V is minus 2, so V is minus 0.5 meters per second. And in the exam I'd make sure you just write down, therefore that's travelling to the left at 0.5 meters per second. In the mark scheme, where are we? So they've let the velocity of Q be V, so you get 1 mark for that, 1 mark for solving it and getting 0.5, and you do need to say in the opposite direction to R, so direction must be made clear. Okay, so part 2, just as object R reaches the edge of the table, it collides with a small object S of mass 3 and is travelling towards R with a speed of 1 in the opposite direction. So this information shown in figure 1.2. The coefficient of restitution in this collision is 0.1, and they want to know the velocities of both of them immediately after the collision. So in this case, it's a very similar thing. We've got R and S again, and let's imagine, well, we don't know either speeds here, so let's call this VR for velocity of R, and this one VS. So first of all, we can do the same thing we did before and use conservation of momentum. So on the beforehand, we've got R is travelling at 4 and it's got mass 2. Just be careful with S, because that's got mass 3, but it's travelling at velocity minus 1 because it's going in the opposite direction. And then on the right, we've got R's mass of 2 and travelling at VR, and S has got a mass of 3 and travelling at VS, we've called it. So this is 8 minus 3, so we've got 5 equals 2VR plus 3VS. Okay, now we can't solve this because it's got two things we need to find out and only one equation. So we're going to use this coefficient of restitution to come up with another equation. So remember the definition of that. So our coefficient of restitution is the speed of separation divided by the speed of approach. So the speed of separation, so here that's going to be Vs minus Vr. So you can always do the velocity on the right minus the velocity on the left. So this one, you could see, well, they're approaching at speed 5 because it's 1 plus 4. If you're not sure about that, you can think of it as minus 1 minus 4, which is minus 5. So the speed of separation is 5. So if we make that look a bit nicer, we know 0.5 equals Vs minus Vr, and now we've got another simultaneous equation. So to solve that, what I'm going to do to start is double this bottom one. So we get 1 equals 2Vs minus 2Vr, because now I've got 2 VRs in both of them. So what I'm going to do, I'm going to add together this one and this one. So on the left, I'm going to have 5 plus 1 is 6. 2 VR is going to cancel out with this minus 2 VR, and we're going to have 5 VS. So our VS is 1.2. Okay, and then all we need to do is sub that. Let's sub it back into this one to work out VR. So 0.5 equals VS minus, VS we can sub in is 1.2 minus VR. So VR will be 0.7, both travelling to the right. Okay, so you get 1 mark for doing your conservation momentum, 1 mark for then getting to that equation, another 2 marks for getting to this equation, and then 2 marks for solving them, and then I'm not bothered about direction. Okay. Right, the table is 0.5 metres above a horizontal floor. After the collision, R and S have no contact with the table. We'll calculate the distance apart of R and S when they reach the floor. So just going back to the original diagram. Where was the original diagram? So we can see essentially these are 2 projectiles now which are falling to the floor, and we want to know how far apart they'll be when they hit the floor. Okay. So we can imagine them projected from the same point. So this is kind of a M1 projectiles question, if you like. So we know both of them are going to hit the floor at the same time. So let's first of all work out what's the time it takes for anything really under gravity to fall 0.4 meters. So S is 0.4, U is 0, V we don't care about, A is 9.8, and T is what we do care about. So I'm going to use S equals UT, which will be 0, plus a half A T squared. So 0.4 over 4.9 will be T squared. So if I square root that, we get T equals 2/7. So they're going to hit the floor after 2/7 of a second. And then if we think horizontally, how far have they travelled? Well, we know that R is travelling, so let's say actually let's say XR because it's horizontal. R was travelling at 0.7, so that will go 0.7 T, or in other words 0.7 times 2/7. So 0.7 times 2/7 is a fifth, so that's gone 0.2 meters. And S was travelling at 1.2. We've got to do that times 2/7 as well. And that gives me a horrible number, 12/35. So if we work out the difference, I'm going to do that minus 0.2, and that gives me 1/7. So that's the difference between these two distances travelled. So that 1/7 of a metre. Okay. So, as they've used R and S separated 0.5 metres a second, I see what they've done. So they've done the same thing as us here. So finding the time, which was 2/7, and then instead of working them out separately, they've worked out, well, if they're separating at 0.5 metres per second, they've just got to do 2/7 times 0.5 to get 1/7. Okay. Right, part B. A particle of mass m bounces off a smooth horizontal plane. The component of velocity of the particle just before the impact is u, parallel to the plane, and v, perpendicular to the plane. Okay, so that's a bit confusing. So at first it's travelling at u this way and v this way. The coefficient of restitution showed that mechanical energy lost in the impact is this, and they've given us a coefficient of restitution is simply E. So what you need to realise is, if this is hitting a plane, so it's going u parallel to the plane and v perpendicular. So I'm going to swap those round because I prefer to, let's imagine our plane here. So it's travelling u like this, v like this, and then after it's hit the plane, it's going to be travelling some speed like that. Now the parallel speed is going to be the same, it's still going to be u, and the speed it's travelling up, well, that's going to be changed by this coefficient of restitution, so that's going to be EV or VE. Okay, so that's just using that whenever you've got something hitting a plane, so this is what's called an oblique impact. The only thing that is affected is the velocity parallel to the plane. So a lot of the time you have to resolve, but here they've given us both. So if we work out the total kinetic energy for both, then we can find the difference, and that's going to be hopefully this. Alright, so think about going to, so beforehand, so the kinetic energy before. Right, so overall, we can think of this having a speed which is going to be like the kind of hypotenuse of v and u. So that would be, let's call this speed, what shall we call it? Well, let's just imagine it's the overall speed before. So it's going to be the square root of all of that. So we're going to have to do half times m times v squared. Now our v is this, so if we square it, we're just going to have v squared plus u squared. And we've got, and then the velocity after, well, we're going to see the same thing here. So this is again going to be the hypotenuse of both of these. So what we're basically doing is taking two velocities and turning them into an overall magnitude. So it's going to be the square root of u squared plus this squared, which is e squared v squared. So we're going to have a similar thing where this is going to be a half m, and then we've got to square this, so we'll get u squared plus e squared v squared. Right, so if we're doing the ke lost then it's going to be the ke before minus the ke after. Right, so we can factorise out a half m from everything, and we're going to have v squared plus u squared minus u squared minus e squared v squared. So nicely these will cancel out, and we've got v squared minus e squared v squared. So we can factorise out v squared as well, and we'll have 1 minus e squared, which I hope and pray is what they've got up here. Yeah. Okay. So we've got some very similar looking diagrams here. So it's going u to the right, and then showing that basically you get a mark for knowing that the speed's going to be the same afterwards. You get a mark for getting that the speed afterwards is going to be EV. A mark for attempt at difference of KEs, so that's kind of what we did there. Clear expansion simplifications, hopefully mine was clear, and then getting to the answer. Right, question 2. Car of mass 1,200 kilograms travels along a road for 2 minutes, during which time it rises a vertical distance of 60 meters. So let's say our car's here, and then it travels along a bit, it goes up a slope which has got a height of 60 meters, and in that time it does 1.8 times 10 to the 6 joules of work against the resistance of its motion. The speed of the car at the start and the end of the 2 minutes is the same, so there's no change in kinetic energy, so that's nice because we can forget about the kinetic energy. So let's think what's happened from when the car is at the bottom of the slope to the top of the slope. Well, so the engine's going to have to put in some work to overcome this friction, so this resistance, if you like, sorry. So that'll be 1,800,000 joules. And then also, it's had to put in energy to get it up the slope. So in other words, there's an increase in GPE. So the engine's also had to put in MGH. So 1,200 times by G times by H, that was 60. So if I work that out, so 1,800,000 plus 1,200 times 9.8 times 60 is 2,505,600 joules. Right, it's done that in 2 minutes, so we can use that energy is power times time. So we're going to have to do the amount of energy we've got divided by the amount of time it took, which was 120 seconds. So no, it wasn't. It was 2 minutes, 120 seconds, which gives me 20,880 watts. So you get a mark for doing the GPE. A mark for using power is work done divided by time. shouldn't really say energy, a mark for using 120 seconds, and a final mark for getting 20,880. Right, the car now travels along a straight, level road. Good. Here's our car, going at 18 meters per second, while developing a constant power of 13.5 kilowatts. Calculate the resistance to motion of the car. Right, so, and then how much work is done against the resistance when the car travels 200 meters. So we know there's some driving force and there's some resistive force. Now we also know these two things must be equal because it's going at a steady speed. So the driving force we can work out using P equals FV. So the power is the driving force times by velocity. So we've got 13,500 equals the driving force times 18. So I'm going to do 13,500 divided by 18, and that gives me 750 newtons. So that must mean that R is also 750 newtons. So I'd make clear that you understand that. Right, how much work is done against resistance? So that we can use doing work done is force times distance. So we've been having to provide a force of 750 newtons over a distance of 200 meters, which is 150,000 joules. Okay, so 1 mark for using P equals FV and getting 750. As V constant, A equals 0, so F minus R equals 0, hence resistance is also that. And you need some justification there. And then using work done is FD, so you get 150 kilojoules. Right, okay, so part 3. While travelling at 18 meters per second, the car starts to go down the slope incline at 5 degrees. So here's our car going at 18 meters per second. It goes down a slope, and now it's travelling at 9 meters per second. And this slope has, let's call it X meters. So the horizontal with power removed and brakes applied. So the total resistance to its motion is now 1,500 newtons. There's no more driving force. Use an energy method to determine how far down the slope the car travels before its speed is halved. Okay, so we know its speed has gone from 18 meters per second to 9 meters per second, and we want to know how far did it take for that to happen. Alright, so if we think about so they've asked us to use an energy method. So let's think about the energy that it has at the start and the end of its journey. So at the start it had a half mv squared kinetic energy, so a half times 1,200 times 18 squared. And at the end it's got a half times 1,200 times 9 squared. But we need to think about where has that energy gone. So to get from here to here, let's think what happened on its journey. So it had to do some work against friction, so it lost this force times distance. So the force was 1,500 and the distance was x. But it will have gained some energy because it's gone down this slope. So it would have gained some potential energy. So it's fallen by this amount. So that's going to be x sine 5. So this distance here. So the amount of energy it will have gained will be m times by g. Sorry about this, it's going to be a bit small, times by h, which was x sine 5. Okay. So you can see now we've got an equation we can solve with x's and stuff in it. So I'm going to bring all the kinetic energies onto the left. So I'm going to do a half times 1,200 times 18 squared, and I'm going to take away a half times 1,200 times 9 squared, and that gives me 145,800 joules. And that's going to equal, I'm going to throw both of these things over, so I've got 1,500x minus 1,200 times 9.8 times x sine 5. So if I factorise out the x, I've got 1,500 minus 1,200 times 9.8 sine 5. So that is 1,200. Check them in degrees times sine 5. About 475x, but I'm going to keep the exact number in my calculator. So x will equal this divided by this, which I've got in my calculator. So 145,800 divided by answer gives me 306.9 meters. Okay. Good. Right, so use of a work energy equation with x, which we've got. So a mark for two kinetic energy terms present, a mark for a GPE with resolution, so using this sine 5, a mark for the GPE term correct, so you get 2 marks in that GPE term, which is good, and a final mark for getting them all correct. So essentially you get 5 out of the 6 marks for getting all these terms together without them even being in an equation. Well, I guess that last mark might be for having it in an equation. And then finally an answer mark for 307 meters. Okay. Right, suppose the car is travelling along a straight level road developing power P. Right, so here's our car. Power P, not force P, so let's call this driving force. And travelling at v meters per second with acceleration A meters per second squared with resistive force R. Show that P equals R plus 1200 A times V and deduce that if P and R are constant, then if A is not 0, it cannot be constant. Right, first of all, show that P equals this. So, right, so if we use, well, we've got to get P into this somehow. So let's think about Newton's second law, because that's going to link together these things, and because we can't say anything's equal at the moment because there's some acceleration. So the overall force to the right is going to be D minus R, and that's going to equal, do they give us a, they don't give us a mass, let's call it M then, and that's going to equal M times A. Now, we also know that power is F times V, but F we've used D, so because it has to be driving force, times by V. So we could say, to get P into this equation, D will be P over V. Right, that looks helpful. MEI. So if we times everything by V, we've got P minus RV equals MAV. This is looking kind of promising. We've got P, we've got an RV, which they've got there, but somehow we've got to get this 1200A. Oh, the car. So we do have a mass. So it's the original car, so M will be 1200. Right, very nice. So P will equal RV plus, so I'm going to put that 1200 now, 1200 AV, and if we factorise out V, we've got R plus 1200 AV. Right, so we also need to answer, so deduce if P and R are constant, then if A is not 0, it cannot be constant. So basically, if P and R are fixed, then if A isn't 0, then it can't be fixed either, basically. So let's have a look at this equation. So if P and R are fixed and A is not 0. So if A isn't 0, that must mean V must be changing. Well, given that if all these things, if P and R are constant, 1200 is a constant, if V changes, then A must change as well. So anyway, let's see what they say. Oh, I haven't got the mark scheme for that bit. So they've got here, if A doesn't equal 0, V is not constant, but P and R are constant, so A cannot be constant. So yeah, you need something wordy to explain that. Right, question 3. Right, so a side view of a freestanding kitchen cupboard and a horizontal floor is shown in figure 3.1. The cupboard consists of a base CE, vertical ends BC and DE, an overhanging horizontal top AD. The dimensions in meters of the cupboard are shown in the figure. The cupboard and contents have a weight of 340 newtons and centre of mass at G. Right, so we know the centre of mass is there, we know the weight is 340 newtons, so I'm going to put that on there. Remember, not 340 G because they've said it's the weight. Calculate the magnitude of the vertical force required at A for the cupboard to be on the point of tipping in the cases when the force acts, so in A, downwards. Right, so let's call this force acting downwards F. So if you've got to think, well, if it's going to tip, if we're acting downwards, where will it tip? So I think that would be about here. Sorry, well, it would be exactly at C, because that would be the corner which it would tip over. So if we think of the kind of forces acting, now there's not going to be any reaction at E because it's on the point of tipping. So we know there's just going to be this weight, which you can imagine acting here. So you can move things along so that they're vertical to the point. And also F, let's bring that down to here. So we know on the point of tipping, the moments of these two will be equal. So in other words, 340 times by 0.5 has got to equal 0.125 F. So 340 divided by 2 is 170. So I'm going to do 170 divided by 0.125 to get 1,360 newtons. Okay, so that's part A. If we were lifting it upwards, whoops, so as they say in part 2, so now our force is acting up like that. So let's move it down here again. So we've got to think, well, where will it be tipping from now? So it would be now at point E. So we can move this force G down again. So this is just a bit trickier to work out the distances. So the distance to the force, the new force F, is going to be 2 plus 0.125, so 2.125 F. And that's got to equal 1.5 times G, so 340. So I've just done 2 minus 0.5 there. So 1.5 times 340 is 510, divided by 2.125 is 240. Okay. Right, so they've got a force BP, so anti-clockwise moment, so you get 1 mark for setting this up, 1 mark for getting the distance is correct. So your method mark is actually for doing moments about C, and you get 1,360. Second one, moments about E, and getting 240. Right, next one, now they've got a force of magnitude Q is applied at A at an angle theta to AB, where cos theta is 5/13, sin theta is 12/13. By considering the vertical and horizontal components at the force A, show the clockwise moments of this force about E is 30Q over 15. Right, so E was down here. So now we've got Q acting at angle theta. So what we can imagine doing is moving this so that the components are at 90 degrees to E. So this component's going to be Q sine theta, and we can move that down here. And then this component, the horizontal one's going to be Q cos theta, and I'm going to be moving it so it's horizontal to E, and that would be there. Okay. And what do they actually ask us? They want to know the clockwise moment of this force about E. So hopefully we get this. So we know cos theta is 5/13, and sine theta is 12/13. So I'm just subbing that in. So working out the clockwise moment about E then. So for this one, the distance there was 2.125 times by 12/13 of Q, and the distance here is 0.9. So 0.9 times 5/13 of Q. And now we just have to hope and pray that that gives us, what was it, 30/13 or something overall. So 2.125 times 12/13 is 51/26, plus 0.9 times 5/13 is 30/13. So we get 30/13 of Q, which is what they wanted. So you get moment expression except S and C. So expect sine and cos interchange, that means. So correct trig ratios or lengths. So for this, and then a mark for getting to that. Right, with the force of magnitude Q acting as shown in figure 3.2, the cupboard is in equilibrium and is on the point of tipping, but not on the point of sliding. Show that Q is 221 and show that the coefficient of friction between the cupboard base and the floor must be greater than 5/8. Right, so let's deal with that Q equaling 221 to start. So we know the overall clockwise force of that about Q is 30/13 Q. So we don't have to worry about any forces now apart from gravity. So we're worrying about E now. So we know clockwise is 30/13 Q, and anti-clockwise is going to be this 340 again. So that's going to be 1.5 times 340. So 1.5 times 340 is 510, and then if we divide that by 30/13, we get 221. So if you solve that equation, we get 221 newtons. Right, now we've also got, we know it's at the point of tipping, but we've got to show the coefficient of friction between the cupboard and the base and the floor must be greater than 5/8. So if we look what's going on, so we've got to kind of imagine now what's going on with friction and things like that. So what I'm going to do is treat this whole cupboard as a point, and then we'll worry about friction and things. So let's try and draw a diagram. So we've got 340 acting this way. We've got friction acting this way because Q is here. And what else? We've got a reaction force. So we've got to link this all together. We can use F equals mu r and then hopefully show that if this is on the point of sliding, then mu must be 5/8. So if we split up Q again, just like we did before, going up we've got Q sine theta, which we know now is 221 times, what was sine? 12/13. And then we've got going this way, Q cos theta, which is Q is 221, cos theta is 5/13. So let's see if we can now work out the reaction force. So that's going to be 221 times 12/13 going up. So we know that 340 has got to equal R plus 204. So R is 136 newtons. And we know that F equals mu R. So that's the maximum F can be, is mu R. So we also know if this isn't moving, that the frictional force must equal 221 times 5/13, which is 85 newtons because we've got equilibrium going left and right. So let's put these together. 85's got to equal mu R, so mu times 136. So mu must be 5/8. Right, good. So if it's not sliding at this point, it's not at the point of sliding, that must mean that mu must be greater than 5/8. So really here we could have said, so F is greater than mu R, 85 is greater than mu over 36. Why am I talking rubbish? Yeah, I've got it the wrong way around. So F must be less than mu r. In other words, the frictional force at the moment must be less than the total possible frictional force, and that gives you that mu must be greater than 5/8. But I think if you do equals and then you justify it at the end, that's fine. So here we've got except less than or equals, and then just make sure you explain yourself at the end. So here they've said F must be less than mu r as not on the point of sliding. So you get a mark for, so this was finding Q to start. Moments equation with all relevant forces, so getting that, then getting to Q, which is 221, so that's 2 of the 9 marks. Let friction be F, normal reaction R, resolve, so that's finding F is 85 like we did, then getting R is 136, so that gets you 4 marks, and then 3 marks for getting to the end. Right, question 4. In this question, coordinates refer to the axes shown in the figures in units, centimetres. Figure 4.1 shows laminar KLMNOP, still can't get the alphabet right, shaded. The laminar is made from uniform metal and has dimensions shown below. Show the x coordinate of the centre of mass of this laminar is 26 and calculate the y coordinate. So we've got to use that. Remember this mx bar. So in other words, the mass of the whole thing equal times by its centre of mass as a coordinate is equal to the sum of all the masses of the individual parts times by their centres of mass. Okay, so we need to split this up into 2 things we can work out the centre of mass of. So I'm going to split it up like this. So first of all, we need the total mass. So that's going to be some year 7 work here. So essentially I'm working out the area of this whole shape. So 40 times 40 plus 60 times 40 gives me 4,000. Or do they give us the mass? No, that's fine. So 4,000 x bar, so I'm going to change the x bar y bar because we're doing it in 2 dimensions, has to equal. Now we split it into 2 parts. So our first one's going to have a mass of 40 times 40, and that's got a centre of mass of 20, 20. The piece above is going to have mass 2,400, and its centre will be 30 on the x, and then it's gone up 20 plus another 20, sorry, it's gone up 40 plus another 20, which is 60. So if we times that all out, so I'll do the x's first. So 1,600 times 20 plus 2,400 times 30 gives 104,000. And then on the bottom, 1,600 times 20 plus 2,400 times 60 is 176,000. So to find x bar, y bar, we've got to divide both by 4,000. So 176,000 divided by 4,000 is 44. Sounds about right. And 104,000 divided by 4,000 is 26, which is what they had. Alright, so they've done it differently to us. They did the whole thing and then took away the piece cut out, it looks like. Either way, if you prefer that way, do it that way, that's fine. So 2 marks for that, a mark for getting x bar and a mark for getting y bar. Right, a uniform thin heavy wire KLMNOPQ is bent into the shape of part of the perimeter of the laminar KLMNOP with an extension of the sides OP to Q. Okay. Show the x coordinate of the centre of mass of this wire is 23.2 and calculate the y coordinate. Alright, so actually this is more complicated because there's more parts to the shape. So now if we work out the total length to get its total mass, so that's 110 plus 40 plus 40 plus that ml will be 20 plus 40 is 250. So its total length is 250, or its mass if you like, times by x bar y bar, and then we're doing the same thing, but I think there's going to be more parts to this. So OP is going to be 110, it's kind of mass, and then its centre of gravity will be 0.55. ON has got a length 40, and its centre of gravity is going to be 20, 0. MN has got mass 40 and centre of gravity, well, the X one's going to be at 40 and Y will be at 20 because it's halfway up. ML has got a length 20 and it's 40 along plus another 10, so that's going to be 50, and it's 40 in the air. Just double check that. Yeah. And finally, going off the page, we've got KL, which has got length 40, and it's going to have, the X is going to be 60 along, and the Y will be, it's 40 already, plus another 20, so 60. Alright, so let's do the X's first. So we've got 100 times 0, plus 40 times 20, plus 40 times 40, plus 20 times 50, plus 40 times 60 is 5,800. And on the bottom, Y is going to be 110 times 55, plus 40 times 0, plus 40 times 20, plus 20 times 40, plus 40 times 60. And that gives me 10,050. So dividing by 250, we get the Y to be 40.2 and the X, moment of truth, is 23.2. Now is that what they had? It is. So wait, did we get 40.2? Yeah, good. Right, so 1 mark for any complete method for CM, so it looks pretty similar to ours there. Any 2 edges, correct mass and centre of mass, or any 4 edges, correct mass and x or y centimetres coordinate correct, and most 1 inconsistent error. Right, the wire is freely suspended from Q and hangs in equilibrium. Draw a diagram indicating the position of the centre of mass of the hanging wire and calculate the angle of QA with the vertical. Right. Now the way I would show this is, instead of trying to draw it kind of hanging from the bracket, so we know it's suspended from, was it OQ? From Q. So we know that the way it's hanging is going to have to go through the centre of mass. So in other words, the centre of mass will be directly below it. So we know the centre of mass is at 23.2, which is a bit along here, and 40.2, so let's say it's about here. So I would just indicate that's 23.2, 40.2, obviously you can draw yours a lot bigger and it will look better than mine. So I'm going to draw a line now connecting them. Well, I'm going to attempt to anyway. There we go. Okay, and I would just indicate on there that this is the vertical, and then you might want to say that's 23.2 and that distance is 40.2. And they also want to know the angle of QO with the vertical. So in other words, this angle here. And I'm just going to draw another diagram there just to be a bit clear. So here's Q, here's the angle we're trying to find, let's call it theta. Here's M. So this distance here is going to be 110 minus 40.2, which is 69.8. This distance here is just 23.2. So tan theta will be 23.2 over 69.8. So if I do inverse tan, I get 18.4 degrees. Okay, so indicate, so your 1 mark there is indicating the centre of mass is vertically below Q, clearly identifying correct angle for 1 mark. Award for arctan, where B is 23.2 and A is 69.8, and they've got 18.4 degrees as well. Alright, a wall-mounted bin with an open top is shown in figure 4.3. The centre part's cross-section KLM and OPQ. The two ends are in the shape of the laminar KLMNOP. The ends are made from the same uniform thin material, each has a mass of 1.5 kilograms. The centre part is made from a different uniform thin metal, has a total mass of 7 kilograms. Okay, calculate the x and y coordinates of the centre of mass of the bin. So if we imagine what's going on here, we've got these two end pieces which are going to have our original centres of mass. So that's these bits here. And then this whole bit that kind of is in the middle, that's got mass 7 kilograms, and that's going to have the centre of mass of our wire we worked out. So if you imagine, if you looked at it dead on, that's in the shape of the wire. So the mass of the whole thing, which is 1.5 plus 7, so 8.5 x bar y bar, has to equal all of that. So these two red pieces have got the same centre of mass, and they've got mass 1.5. So if you like, there's two of them, so we could say that's 3 lots, 3 kilograms times by xy. So let's just go back and find out what that was. So that was 26.44. And the blue bit in the middle, which is mass 7, will have the centre of mass of the other bit, which was 23.2, 40.2. So if you like, we're doing exactly the same as we did in parts 1 and 2, it's just that the 3 bits are the 2 end pieces and the bit in the middle. So for x bar, I'm going to do 3 times 26 plus 7 times 23.2, so that would be 240.4, and I'm going to divide it by 8.5 because I've got to divide it by this mass, and that gives me 28.3, so there's 3 significant figures. And then for y bar, I'm going to do 3 times 44 plus 7 times 40.2, divided by 8.5, and that gives me 48.6 to 3 significant figures. Okay. What have I done wrong here? I got the original mass wrong. So all I did was 7 plus 1.5, but because there's 2 end pieces, that should have been 10. Right, so let me run through that again. 3 times 26 plus 7 times 23.2 divided by 10 is 24.04. And then 3 times 44 plus 7 times 40.2 divided by 10 is 41.34. Okay. So combining the parts using masses, one for using both ends, which I would have lost that mark because I only had 8.5. A1 for it all correct, and then that for 2 answers. And you get, even if you messed up the other 2 parts, you still get follow through marks for your original Y values, which is usually the case, so don't be too scared if you're not. Right, I hope you found that useful. As always, please let me know if you've got any other videos you'd like in the future. Cheers.